Hello everyone. So we had finished with the first section of this webbook, which was using neural nets to recognize handwritten digits. Now we're going to start the second section, which was how the backpropagation algorithm works. So in the first section, we treated the backpropagation algorithm as sort of a black box and did not go in depth into how it works. So here we'll study about that. Excuse me. In the last chapter, we saw how neural networks can learn their weights and biases using the gradient descent algorithm. There was, however, a gap in our explanation. We did not discuss how to compute the gradient of the cost function, and that is quite a gap. In this chapter, I will explain a fast algorithm for computing such gradients, an algorithm known as backpropagation. The backpropagation algorithm was originally introduced in the 1970s, but its importance wasn't fully appreciated until a famous 1986 paper by David Rumelhart, Jeffrey Hinton, and Ronald Williams. As a fun fact, Jeffrey Hinton also taught a Coursera course in which he proposed an algorithm known as RMS prop. And today, RMS prop is it is one of the famous optimizers like Adam and all. So Andrew Ng mentioned this in one of his videos. That paper describes several neural networks where backpropagation works for faster than earlier approaches to learning, making it possible to use neural nets to solve problems which had previously been insoluble. Today, the backpropagation algorithm is the workhouse of learning in neural networks. Okay, so I also plan to cover research papers at some later point, so this could be a good starting place. This chapter is more mathematically involved than the rest of the book. If you are not crazy about mathematics, you may be tempted to skip the chapter and to treat backpropagation as a black box whose details you are willing to ignore. Why take the time to study those details? The reason, of course, is understanding. At the heart of backpropagation is an expression for the partial derivative of the cost function with respect to the weight, which is the partial derivative of the cost function with respect to the weight or bias B in the network. The expression tells us how quickly the cost changes tells us how quickly the cost changes when we change the weights and biases. And while the expression is somewhat complex, it also has a beauty to it, with each element having a natural intuitive interpretation. And so backpropagation isn't just a fast algorithm for learning, it actually gives us detailed insight into how changing the weights and biases changes the overall behavior of the network. That's well worth studying in detail. With that said, if you want to skim the chapter or jump straight to the next chapter, that's fine. I've written the rest of the book to be accessible even if you treat back propagation as a black box. There are, of course, points later in the book where I refer back to results from this chapter, but at those points, you should still be able to understand the main conclusions even if you don't follow all the reasoning. So, warm up, a fast matrix based approach to computing the output from a neural network. Before discussing back propagation, let us warm up with a fast matrix-based algorithm to compute the output from a neural network. We actually already briefly saw this algorithm near the end of the last chapter, but I described it quickly, so it's worth revisiting in detail. In particular, there is a good way of getting comfortable with the notation used in back propagation in a familiar context. So let us begin with a notation which lets us refer to weights in the network in an unambiguous way. We'll use WJKL. So I don't know how to pronounce this exactly, so I'll pronounce this WJKL to denote the weight for the connection from the kth neuron in the L-1th layer to the jth neuron in the Lth layer. So for example, the diagram below shows the weight of a connection from the fourth neuron in the second layer to the second neuron in the third layer. So fourth neuron is in the previous layer, so it is the kth neuron which comes afterwards, and the jth neuron which is the in the layer after comes before. So this connection from the fourth neuron of layer 2 to the second neuron of layer 3 would be represented as W24 and superscript 3, where 3 represents the layer which is ahead, right? So if you are evaluating the representation for a connection between two layers, you will take the superscript for the layer which is ahead, the layer to which the arrow is pointing. This notation is cubism at first, and it does take some work to master. but with a little effort you will find the notation become easy and natural. One quirk of the notation is the ordering of J and K indices. You might think that it makes more sense to use J to refer to the input neuron and K to the output neuron, not vice versa, as is actually done. I will explain the reason for this quirk below. So this simply is telling you that wouldn't it be more natural if the 4 was before and the 2 was after, as the 4 comes before in the network and the 2 comes after. But he says that this using this specific notation will help us gain some things later. So here's the reasoning. We use a similar notation for the network's biases and activations. Explicitly, we use BJL for the bias of the jth neuron in the LH layer and AJL for the activation of the jth neuron in the LH layer. So the layer is always indicated by the superscript. The following diagram shows example. So this is the third neuron of the second, the bias for the third neuron in the second layer, and this is the activation for the first neuron in the third layer. With these notations, the activation AJL of the jth neuron in the LH layer is related to the activations in the L-1th layer by the equation. Okay, so this is easy to grasp. This is the activation of the jth neuron in the LH layer, and this is sigmoid, just the activation function. And inside it, you have the weights which are connecting it to the jth neuron. So for the different case, you are going to sum over them and use the activations from the previous neuron. So to what's happening? So just to give an example, if we take this case right here, so if you have A31, your J is 1, right? So when you do all your calculations, you will have W 1 1, 1 2, 1 3, 1 4 respectively multiplied by A1, A2, A3, A4 from the L minus 1th layer. So this is just taking these individual neurons and weighing them up, and then of course adding the bias where the sum is over all neurons k in the L-1th layer. To rewrite the expression in the matrix form, we define a weight matrix WL for each layer L. The entries of the weight matrix WL are just the weights connecting to the Lth layer of the neuron. That is, the entry in the jth row and kth column is WJKL. So this is why this makes sense, having the k afterwards, because when you talk about matrices, generally we talk in a row by column sense. So this makes this notation consistent with the matrix notation. Similarly, for each layer L, we define a bias vector BL. You can probably guess how this works. The component of the bias vector adjusts the values BJL, one component for each neuron in the LX layer. And finally, we define an activation vector AL, whose components are the activation AJL. So I hope this makes sense. The last ingredient we need to rewrite 23. So this particular equation in the matrix form. In a matrix form is the idea of vectorizing a function such as sigmoid. We met vectorization briefly in last chapter, but to recap, the idea is that we want to apply a function such as sigmoid to every element in a vector V. We use the obvious notation sigmoid of V to denote this element-wise application of a function. That is, the components of sigmoid V are just sigmoid Vj is sigmoid of the jth entry. So I hope this makes sense. As an example, if you have the following function f of x square, so the vectorized representation would be just inputting this and then individually taking the function and applying them to each of the entries as we've done here, and you get 4 and 9. That is the vectorized f just squares every element of the vector. With these notations in mind, equation 23 can be rewritten in the beautiful and compact vectorized form. So now that entire summation is now a matrix product, right? And you can see this is a lot more simpler and a lot more convenient to deal with. This expression gives us a much more global way of thinking about how the activations in one layer relate to activation in the previous layer. We just applied a weight matrix to the activation, then add the bias, and finally apply the sigmoid function. By the way, it's this expression that motivates the quirk in WJKL notation mentioned earlier. If we use J to index the input and K to index the output, then we need to replace the weight matrix by the transpose of the weight matrix. That's a small change but annoying, and we would lose the easy simplicity of saying and thinking apply the weight matrix to the activations. So I think this is a good point, and in some places you might even see the transpose notation being used. So once you have the basic idea of what is really happening, I believe it will be easy to grasp anyway. That global view is often easier and more succinct and involves fewer indices than the neuron by neuron view that we've taken to now. Think of it as a way of escaping index hall while remaining precise about what's going on. The expression is also useful in practice because most matrix libraries provide fast ways of implementing matrix multiplication, vector addition, and vectorization. Indeed, the code in the last chapter made implicit use of this expression to compute the behavior of the network. So the code, which does he pinpoint the specific line? No. So in the code was in fact using these equations only. The code was using, if I can get that part here. The Okay, I accidentally shifted the screencasting range. Okay, so if we go to the backpropagation section, I believe he had given us the code, but I cannot find it right now. Where is it? Load data is here. Yeah. So you can see that you're in fact doing a taking the W as like a entire matrix in activation and applying np dot dot to them. So the code was using this. Okay, so when using equation 25, this one to compute AL, we compute the intermediate quantity ZL along the way. This quantity turns out to be useful to be worth naming. We call ZL the weighted input to the neurons in layer L. We'll make considerable use of the weighted input ZL in the later in the chapter. And equation 25 is sometimes written in the terms of the way input as AL is sigmoid of ZL. I hope this makes sense. You're just taking this entire thing and substituting ZL. Also, the components are just like the previous thing. ZLJ is this summation and using the summation notation. So ZLJ is just the weighted input to the activation function for neuron J in layer L. So just take this thing, and if you substitute this with ZLJ, you get the specific input to a particular neuron, and if you use the matrix notation, you get like a vector of inputs to all the neurons. The two assumptions we need about the cost function. The goal of backpropagation is to compute the partial derivatives del C by del W and del C by del B of the cost function C with respect to weight W or bias B in the network. For backpropagation to work, we need to make two main assumptions about the form of the cost function. Before stating those assumptions though, it's useful to have an example cost function in mind. We'll use the quadratic cost from the last chapter. In the notation of the last section, the quadratic cost has the following form. In the notation of the last section, sorry, I misread this as last chapter. So now this is the activation function where n is the total number of training examples. The sum is over individual training examples. X, y is equal to y of x is the corresponding desired output. L denotes the number of layers in the network, and AL is equal to ALX is the vector of activation output from the network when X is the input. So this just is applying the activation. Okay, so what assumptions do we need to make about the cost function C in order for the backpropagation can be applied? The first assumption we need is that the cost function can be written as an average. So instead of doing everything, we are taking the average over the cost functions for individual training examples. So I guess he'll explain why later. This is the case for the quadratic cost function where the cost for a single training example is this. So the average cost would be the average over all training examples. This assumption will also hold true for all other cost function we will meet in this book. The reason we need this assumption is because what backpropagation actually does is to compute a partial derivative of the components for or for a single training example, and using that we then recover the entire partial derivative by averaging over training examples. In fact, with this assumption in mind, we'll suppose the training example x has been fixed and drop the x subscript, writing the cost c of x as c. We'll eventually put the x back in, but for now it's a notational nuisance that is better left implicit. So this was also pretty self-explanatory, I think. They're just saying that to compute the average over all the training examples, we can compute the partial derivatives over specific examples and then take the average. The second assumption we make about the cost is that it can be written as a function of output from the neural network. For example, the quadratic cost function satisfies this requirement, since the quadratic cost for a single training example x may be written as this. Uh, Let us just read this again. It can be written as a function of outputs from the neural network. Okay, so and thus is a function of the output activations because you have this term. Of course, this cost function also depends on the desired output y, and you may wonder why we are not regarding the cost function also as a function of y. Remember that the input training example x is fixed, and so the output y is also fixed. In particular, it's not something we can modify by changing the weights and biases in any way. That is, it's not something that which the neural network learns, and so it makes sense to regard C as a function of the output activations AL alone, with Y merely a parameter that helps to define the function. Okay, so now we have the Hadamard product. The backpropagation algorithm is based on common linear algebraic operations, things like vector addition, multiplying a vector by a matrix, and so on. But one of the operations is a little less commonly used. In particular, suppose S and T are two vectors of the same dimension, then we use S Hadamard T to denote the element-wise product of the two vectors. Thus, the components of S element-wise product T are just taking the individual components and multiplying them up. As an example, if you have this, then you take 1 and 3, multiply them, 2 and 4, multiply them, and get this. This kind of element-wise multiplication is sometimes called a Hadamard product or square product. We'll refer to it as a Hadamard product. Good matrix libraries usually provide fast implementation of the Hadamard product, and that comes in handy when implementing backpropagation. Okay, so you might be wondering what are good matrix libraries. So programming languages have certain constructs. So many of them have certain inbuilt libraries which implement a lot of functions for you. So you do not need to go ahead and implement everything from scratch every time you want to make a new neural network. So this is what they mean by good libraries. Okay, so should I cover this section as well in this video? I'll just check what the length of the video already is. Okay, we have time, so I'll cover this one also. The four fundamental equations behind backpropagation. Backpropagation is about understanding how changing the weights and biases in a network changes the cost function. Ultimately, this means computing the partial derivatives, but to compute those, we first introduce an intermediate quantity, delta JL, which we call the error in the jth neuron in the LH layer. Backpropagation will give us a procedure to compute this error, and then we'll relate the error to the partial derivatives. So they are now introducing a new quantity, which would be the error in the jth neuron in LH layer, in the LH layer. Okay, so now they are going to define what the error really is. To understand how the error is defined, imagine there is a daemon in a neural network. The daemon sits at the jth neuron in layer L. As the input to the neuron comes in, the daemon messes with the neuron's operation. It adds a little change delta ZJL to the neuron's weighted input, so that instead of outputting the sigmoid of delta ZJL, the neuron instead outputs the sigmoid of ZJL plus delta ZJL. This change propagates through later layers in the network, finally causing the overall cost to change by this factor. So this factor, you might have seen such similar factors before also, and you might be familiar with these sorts of expressions if you've studied like error analysis in physics or somewhere else. So essentially what this daemon is doing is the previous neurons have input their weighted sum into the neuron of the next layer, and this neuron then applies the activation function and supplies it to the subsequent layers or the output. So the daemon here is taking all the input it is getting already and then adding a small quantity itself, and this small quantity then affects the output of the neuron J in layer L. So now this daemon is a good daemon and is trying to help you improve the cost. That is, they are trying to find a value of delta ZJL which makes the cost smaller. Suppose the partial derivative of C with respect to ZJL has a large value. either positive or negative. Then the daemon can lower the cost quite a bit by choosing ZGL to have an opposite sign to this. So essentially you want to minimize the cost function, right? So if you have a large value, a large positive value, then it will take a negative value and add it. So essentially it will bring this down. And if you have a large negative value, then it will choose a positive value of delta ZJL. By contrast, if the partial derivative of C with respect to ZJL is close to 0, then the daemon can't improve the cost much at all by, by perturbing the weighted input ZJL. So far as the daemon can tell, the neuron is already pretty much optimal. And so there's a heuristic sense in which delta CJL is a measure of the error in the neuron. So I hope you got what they're trying to convey. Delta ZJL, sorry, the partial derivative of C with respect to ZJL is being compared to the error in the neuron, which the daemon is trying to minimize. So it is trying to add such a value of delta ZJL to bring down this error. And if the error is highly positive, then it will add a negative value. If the error is highly negative, then it will add a positive value. But the problem comes in when this error is already quite small. So the daemon might end up adding something and it might make the error even worse. So like if the error is negative 0.001 and the daemon adds a 2 to fix the error, then it is more erroneous than it was before. So for the daemon, when the cost is nearby uh, 0, then the daemon already thinks that it is pretty much optimal. And this is only the case for small changes to delta ZJL, of course. We'll assume that a daemon is constrained to make such small changes. Okay, so motivated by this story, we defined the error delta JL of the neuron J in layer L by this term, which was the error in context of the daemon. As per our usual conventions, we use delta L to denote the vector of errors associated with layer L. So the first entry will be the error associated with the first neuron of layer L, then the second, then the third, and so on. Backpropagation will give us a way of computing delta L for every layer and then relating those errors to the quantities of real interest. So the partial derivative of C with respect to WJKL and the partial derivative of C with respect to BJL. So the weights, so just to revise, this is the partial derivative of the cost function with respect to the weight of the neuron, uh, weight connecting the neuron in the kth neuron of the L minus 1th layer to the jth neuron of the Lth layer. And this is the partial derivative of the bias associated with the jth neuron of the Lth layer. You might wonder why the daemon is changing the weighted input ZJL. Surely, it would be more natural to imagine a daemon changing the output activation AJL, with the result that we'd be using the partial derivative of C with respect to AJL as a measure of error. In fact, if you do this, things work out quite similarly to the discussion below. But it turns out to make the presentation of backpropagation a little more algebraically complicated. Okay, so that would make it more complicated. So we'll stick with this measure, where you take the partial derivative with respect to the pre-activation value and not the post-activation value of the jth neuron of the Lth layer. In classification problems like MNIST, the term error is sometimes used to mean the classification failure rate. For example, in the neural net, if the neural net correctly classifies 96% of the digits, then the error is 4%. Obviously, this has quite a different meaning from our delta vectors. In practice, you shouldn't have trouble telling which meaning is intended in any given usage. Okay, so now we have a plan of attack. Backpropagation is based around four fundamental equations. Together, those equations give us a way of computing both the error delta L and the gradient of the cost function. I state the four equations below. Be warned though, you shouldn't expect to instantaneously assimilate the equations. Such an expectation will lead to disappointment. In fact, the backpropagation equations are so rich that understanding them will require considerable time and patience as you gradually delve deeper into the equations. The good news is that such patience is repaid over time, and so the discussion in this section is merely a beginning, helping you on your way to a thorough understanding of the equations. So here's a preview of the way we'll delve more deeply into the equations later in this chapter. I'll give a short proof of the equations which helps explain why they are true, We'll restate the equations in algorithmic form as pseudocode and see how the pseudocode can be implemented as real running Python code. And in the final section of the chapter, we'll develop an intuitive picture of what the backpropagation equations mean and how someone might rediscover them from scratch. Along the way, we'll return repeatedly to the four fundamental equations as you deepen your understanding. Those equations will come to seem comfortable and perhaps even beautiful and natural. Okay, so where should we stop for this session? Okay, so we'll stop here. So we'll finish off this section. So let's have a look. Did I go a bit too far up? Yep. So we were here. We had finished this. An equation for the error in the output layer delta L. The components of delta L are given below. So the jth component is the partial derivative of C with respect to the activation function times the sigmoid derivative of sigmoid with respect to uh, of the jth neuron in the Lth layer. Okay, so this is a very natural expression. The first term on the right just measures how fast the cost is changing as a function of the jth output activation. If, for example, C doesn't depend much on a particular output neuron J, then the partial derivative of the jth neuron on LH layer will be small, which is what we would expect. The second term on the right, the sigmoid derivative of sigmoid of the pre-activation value of the GH neuron in LH layer measures how fast the activation function sigmoid is changing at this particular value. So this is very simple if you are familiar with partial derivatives and you remember that our definition for the error in the JH neuron of LH layer was a partial derivative of C with respect to the ZJL, right? Del C upon del ZJL. But if you remember, the cost function has one extra layer between ZJL and the output, which is the activation function. So the cost function can be expressed as the activation function applied on ZJL. So in this context, you are first taking the derivative with respect to the activated value, and then using the chain rule you take the derivative of this with respect to ZJL, which gives you this term. Okay, so if you're not familiar with chain rule, then you can study that somewhere. I guess I think 3 Blue 1 Brown also has a great video on chain rule, and Khan Academy, of course. So this is somewhat what we are doing. We are representing the dy by dx as dy by first the derivative with respect to the activation function, then like the value obtained after the activation, and then the derivative of the value obtained after the activation with respect to the value get you got before the activation. That is the weighted input to the neuron. Okay, so I hope that makes sense. If, for example, C doesn't depend much on a particular output neuron J, then this would be small, of course, which is what we would expect. The second term on the right, the sigmoid ZJL, the derivative of sigmoid ZJL measures how fast the activation function sigmoid is changing at ZJL. So if you're familiar with derivatives, first of all, this is the Newton notation. There are two notations. The more commonly seen one, which is the dy by dx kind, is the Leibniz notation, but this prime notation is Newton's notation, and uh, when you're dealing with like obvious derivatives, then I prefer this notation because it is quite small. But I hope this makes sense. Notice that this equation is easily computed. In particular, we compute ZJL while computing the behavior of the network, and it's only a small additional overhead to compute the the value of the derivative of sigmoid at the particular point. The exact form of this partial derivative will of course depend on the form of the cost function. However, provided the cost function is known, there should be little trouble computing this derivative. For example, if you're using the quadratic cost, and so this is obviously computable. So this is why now you can uh, understand why the half comes into handy. When you take the derivative, this 2 comes here, and this 2 and half, the 2 in the numerator and denominator get cancelled out. Okay, so equation one this the first equation of backpropagation is a component-wise expression for delta L. It's a perfectly good expression, but not the matrix-based form we need for backpropagation. However, it's easy to rewrite the equation in a matrix-based form as this. Here, the nabla AC is defined to be a vector whose components are the partial derivatives with so the partial derivatives of the cost function with respect to the activations. You can think of this as expressing the rate of change C with respect to output activations. It is easy to see these equations are equivalent, and for both reasons, and for that reason, from now we'll use these equations interchangeably to refer to both equations. As an example, in this case of quadratic cost, we have this derivative as this al minus y, which you had computed here, the gradient. And so the matrix based equation would be al minus y and the Hadamard product with the derivative of the sigmoid function at location zl. And now you see that we have a nice vector form, and this vector form can easily be computed by a matrix library such as numpy. Okay, so I hope this makes sense. So now moving on, an equation for delta L in terms of error in the next layer, delta L plus 1. So now we are at the second equation of backpropagation. So now you have delta L, the error, which is expressed as, okay, so I W superscript L plus 1, the transpose, then you take the matrix multiplication with delta L plus 1, take the Hadamard product with the derivative of sigmoid at GL. But let's read this, and which would make much more sense than blindly reading out the formula, where WL plus 1 transpose is the transpose of the weight matrix WL plus 1 for the L plus 1th layer. This equation appears complicated, but each term has a nice interpretation. So if you this weight matrix would be the matrix which you use to compute the values in that particular layer. So now, suppose we know that error delta L plus 1 at the L plus 1th layer. When we apply the transpose weight matrix, we can think intuitively of this as moving the error backward through the network, giving us some sort of measure of the error at the output of LH layer. We then take the Hadamard product with this derivative of the sigmoid at ZL. This moves the error backward through the activation function layer L, giving us the error sigmoid del L in the weighted input to layer L. Okay, so this was a huge thing to take in, I guess, but let's just explain what happens. So essentially, they are trying to get the error at a previous layer when you have the error at the next layer. Okay, so why this is important, we'll probably get to that. But how is this holding? Let's just understand that first. So had you taken this matrix in the non-transpose form, then you would have used this to compute the values in the layer. But the transpose form is akin to going backward, and you can think of this intuitively as moving the error backward through the network. So once you take the matrix multiplication with the error in the L plus 1th layer, you get you get some sort of measure of the error at output of the LS layer. And then when you take the Hadamard product with the derivative of sigmoid at point ZL, this moves the error back one more step. So here, up until here, you can think of this as being just at you have the error after the activation is done, but doing this you get the move back one more step and go to the place where the activations have not yet been done. So you have the error pre-activation, so you have the error in the weighted input to the layer. So by combining the equation 1 and equation 2 of backpropagation, we can compute error delta L. Okay, so they are overlapping for any layer in the network. We can start by using equation 1 to compute delta L, and then apply the equation to get delta L minus 1, and then delta L minus 2, and so on. Okay, so now we have the third equation of backpropagation. An equation for the rate of change of the cost with respect to any bias in the network. In particular, the partial derivative of the cost function with respect to the bias of the jth neuron in the LH layer is delta JL. That is, the error delta JL is exactly equal to the rate of change of this. This is great news because these equations have already told us how you can compute this delta. So we can in fact now easily get the partial derivative of c with respect to the bias b. And now when you write this in shorthand, then it is like reasonable to assume that you will understand that you are getting the error at the same location as where you're taking the bias. It can't be like you're taking the first layer of the first neuron of the third layer and getting the error for the seventh neuron of the third layer, right? So now we are at the fourth equation of backpropagation, an equation for the rate of change of the cost with respect to any weight in the network. In particular, the partial derivative of c with respect to the weight connecting the kth neuron of L minus 1th layer to the jth neuron of Lth layer is this, which is the activation of the kth neuron of L minus 1th layer times the error in the jth neuron of Lth layer. So before I move ahead, I'd really recommend, if you're grasping what these notations are, and if you are not, then I'll highly recommend opening the blog post just as a side tab and going scrolling down to the section where they define the notations and following along as I speak. And even if I make some error somewhere, then do pinpoint them in the comments. This tells us how to compute the partial derivatives in terms of the quantities delta L and AL minus 1, which we already know. So you're computing the derivative of the cost function with respect to the weight, and now you're getting them in terms of delta L and AL minus 1, which you already know. So the equation can be rewritten in a less index heavy way. So you have the partial derivative of c with respect to the weight as the activation of the input times the error of the output, where it's understood that A in is the activation of the neuron input to the weight W, and del out is the error in the output neuron from the weight W. Zooming in to look at just the weight W and the two neurons connected by the weight, this is the thing. So A in, del out, and this. A nice consequence of equation 32, which is this, is that when the activation A in is small, the gradient, so the change in cost with respect to weight will also tend to be small. In this case, we'll see that the weight learns slowly, meaning that it's not changing much during gradient descent. In other words, one consequence of backpropagation equation 4 is that weight's output from low activation neurons learn slowly. Okay, so you might also feel that this is intuitive. If the neuron is slightly activated, then it is in some sense learning slowly because it is not being activated as much as its peers. And you might also now understand, because these partial derivatives are just a representation of the change, right? So if this value of the post activation is small, then uh, like this change is also small. So you see that uh, it will not change much if you make some changes in the weight. So you'll see that the model will learn its weight slowly, because you will not have like some significant changes at the output immediately. You will have to tweak the weights much more than if the model would have reciprocated more to changes. Okay. So now there are other insights along these lines which can be obtained from the equations backpropagation 1 to 4. Let's start by looking at the output layer. Consider the term the derivative of the sigmoid ZJL. Recall from the graph of the sigmoid that the sigmoid becomes very flat when ZJL is approximately 0 or 1. So at these points the slope would be 0. So this term would be 0, right? And so the lesson in that, wait, okay, if I can open this graph, so you can see that the slope here is 0. So weight in the final level learns slowly if the output neuron is either low activation or high activation. So I hope this makes sense. In this case, it's common to say that the output neuron has saturated, and as a result the weight has stopped learning or is learning slowly. Similar remarks hold for the biases of output neurons. Okay, so I hope this makes sense. We can obtain similar insights for earlier layers. In particular note, this term is also present in the equation, the second equation of backpropagation. This means that the error in the jth LS layer is small if the neuron is near saturation. And this in turn means that any weights input to the saturated neuron will learn slowly. Okay, this reasoning won't hold if this value is large, has large enough entries to compensate for the smallness, but he's speaking in a general sense. Summing up, we've learned that a weight will learn slowly if either the input neuron is low activation or if the output neuron has saturated. None of the observation is too greatly surprising. Still, they help improve our neural network of what's going on as a neural network learns. Furthermore, we can you turn this type of reasoning around. The four fundamental equations turn out to hold for any activation function and not just the standard sigmoid function. So wherever you had the derivative to sigmoid, you will have the derivative of the other activation functions. That's because, as we'll see in a moment, the proofs don't use any special properties of sigmoid, and so we can use these equations to design activation functions which have particular desired learning properties. As an example, to give you an idea, we were to choose a non-sigmoid activation function sigmoid so that the partial derivative is all sigma, so that the partial derivative is always positive and never gets close to zero. This would prevent the slowdown of learning that occurs when ordinary sigmoid neurons saturate. Later in this book, we'll see examples where this kind of modification is made to the activation function. Keeping the four equations in mind uh, can help explain why the modifications are tried and what impact they can have. So these are the four equations of backpropagation. Okay, so the problems, I guess I'll start them in the next video. I'll start off with them because it's frankly getting quite long, the video. And I hope you enjoyed this, and let's continue this again.